Now we'll begin section 9.2 on estimating a population mean. Our objectives are to use our calculators to construct a confidence interval estimate now of a mean, not proportion now, but mean. And we will learn how to calculate the sample size required to estimate a population mean. To estimate a population proportion, we have to have population. That should say mean. To estimate a population mean, caught a mistake there, we must have quantitative data. Remember, for proportion, it said qualitative data with two outcomes. So those were categories like somebody's left-handed or they're not left-handed. Now we're talking about quantitative data, things we measure or count, quantities, right? So make sure you fix that to say mean. When estimating the population mean, there are three main ideas. Number one, the sample mean, and let's put our symbol for that, X bar, right here, just as a reminder, is the best point estimate of the population mean mu. A point estimate is one value that we use to estimate the population mean, and if we have a sample, that one value would be the sample mean. But what we'll find in this section, of course, and what we're learning in chapter 9, is that a better way to estimate is to estimate with an interval. So we can use the sample mean, and again, let's just put that X bar as a reminder, to construct a confidence interval estimate of the true value of the population mean. And we can find the sample size. That's our last thing we'll do. And remember that symbol, if you want to put it nearby, is lowercase n. We can find the sample size necessary to estimate the population mean mu. There are certain requirements for estimating a population mean. The sample must be a simple random sample. And remember, I often use SRS as an abbreviation for that. Then either or both of these conditions must be satisfied. Could be just A, could be just B, could be both. The population is normally distributed. So if it's normally distributed, you're good to go. Normally distributed is what I was trying to say. Or the sample size is greater than 30. That might remind you of the central limit theorem, which is what that is, that we spoke of before, where if you have a normally distributed population, it doesn't matter what your sample size is. But if you don't, or you don't even know what your population is, how it's distributed, then you just have to have a sample size greater than 30. But of course, you could have normally distributed and a sample size greater than 30. That's perfectly fine. Okay, the larger the sample size, the more resistant the mean is to non-normal conditions. All that says is if n gets bigger and you have a non-normal distribution, maybe it's uniform, maybe it's skewed one way or the other, it will, if your sample size is large enough, it will resist that non-normal condition. It'll act more like a normal distribution, which is what we want, right? So we can use things like normal CDF and other theorems and formulas and things we're learning that require that it be behave like a normal distribution. Okay. A statistical procedure is robust if it is accurate despite minor departures from the model requirements, such as normality. So one of our requirements is normality, and our procedure is robust if it's accurate, even if there are minor departures from that normality. For this, for finding the confidence interval estimate for the population mean, we will use the T, is also called the student T, distribution. Since we don't have sigma. So if we had sigma, we would use a Z distribution, but we don't. So we have to use the T distribution. Common confidence levels, we've seen this before, and we're just going to write it again. Remember, 90% is common with an alpha of 10%. Of course, we'll write it as 0.01. 95% with an alpha of 0.05 or 5%. Which then we would write as 0.05. I'm just used to writing it as a decimal. But I'm trying to show you where that's coming from. And 99%, so alpha would be 1%, and as a decimal, 0.01. Those are the common ones we'll see. Now, you will not need this formula below here about how the margin of error, where E comes from. Again, we're going to have a margin of error because we're constructing a confidence interval. It's different than the one for the proportion. The calculation is. You won't need to do this. This is programmed in your calculator, but this is to help us understand where the calculator, how the calculator is going to work, what information it's going to need from us. So remember, we're going to be constructing a confidence interval about mu, where we have our sample mean minus the margin of error is the lower bound, and our sample mean plus the margin of error will be the upper bound. And the calculator is just going to give you, as before, a lower bound and an upper bound. But we've got to give it some information. Obviously, you can see some of the things that are being needed. This alpha, we won't type in alpha, but we'll type in the confidence level, and the calculator will get alpha from that. So we will need to give the calculator the confidence level. You can see it's asking for S, the sample standard deviation. You can see it's asking for N, the sample size, and we'll need to give X bar because once E is calculated, the calculator has to subtract E from X bar to give you your lower bound and add E to X bar to give you the upper bound. So we'll have to give X bar. So this is the information needed for the calculator: confidence level, sample standard deviation, sample size, sample mean.